Convergent series and crispy nuggets. Say it's a bright sunny day and you're out for a walk, daydreaming about chicken nuggets like you always do. And you happen to meet Suki the nugget. You exchange pleasantries and turns out Suki is enthusiastic about mathematics as well. So, do you want to learn about series and their convergence? Oh well, then here goes. In mathematics, physics, economics, or other daily life routines like nugget eating, sometimes you face infinite series. That is, addition of infinite terms, generally, if you're lucky, defined by an nth term. And it becomes really interesting to see whether the summation gives a finite number or infinity. If you get a finite number upon adding all the terms, you say that the series converges. And in case, well, if you're unlucky and the summation gives you infinity, you say that the series diverges. What? Wait. Hold on. What is this nth term? What's un? What's going on? So summation un would mean that I'm taking the sum from u1, u2, u3 going on to un. And if for a function where n tends to infinity, that is, I'm considering infinitely many terms, and if then my summation tends to a certain value, a finite number, then I say that my series is convergent. Wait. So you mean even if I'm adding like infinitely many number of terms, I can still get a finite value? Is that even what? Actually, yep, that's right. For these really cool and special convergent series, adding infinitely many terms will in fact give you a finite answer. Whoa, that's so cool, but like how? Oh well, I guess I'll have to use an example. Say, do you like eating nuggets? To which, by the way, I hope you're gonna say yes, because otherwise, I mean, what's the point of life? Okay then. But first, let's try our intuition for a bit. You have a series, summation u of n, and you take the summation till the ith term. What I mean by this is that Si is equals to u1 plus u2 plus u3 going on to u of I. So this sum is then called the partial sum, and note that this will always be a finite number because you know that you're adding a finite many terms. So when you do see such a series in life, ask their partial sum with, of course, respect. Hello, milady series. Hello. So ask them, how do you look if I take summation from 1 to ith term as compared to when I take summation from 1 to I plus 1th term? What I mean by that is that let's say I'm taking the summation till the ith index and then a summation till the I plus 1th index. Then if as I tends to infinity, that is I goes for a very large number, do they start looking similar? Note that if that does happen, then it means that as I'm adding more number of terms, every new term added has a smaller and smaller contribution to the entire sum. So then I can sort of say that limit s of I when I tends to infinity goes to a finite number, which is to say that my summations Si or the partial sums start converging to a finite value. Note that something cute that automatically follows is that if every new term added in the summation has a smaller and smaller contribution to the total sum, then if we incorporate infinitely many elements, the last or the infiniteth term's contribution must tend to 0, which is just another way of saying that limit n tends to infinity of un should be equals to this cute little pretty 0. So consider this series, which quite fashionably is called the geometric progression series, where you're just multiplying a multiplicative factor r in each term. So the summation is a plus ar square plus ar cube and so on. So what do you think should be the sum of this? Let's break this down to two parts. If r is greater than 1, then r square is obviously greater than r, and r cube is greater than r square, and so on, which means that every term that you're adding is actually a bigger term. So quite clearly you can see that this would diverge and would tend to infinity. Well, let's consider the more interesting case of r less than 1. As you can see that I've written the summation as s, that is s is equal to a plus r square plus ar cube and so on. And then in equation 2, I multiply the same equation by a multiplicative factor r and then slightly shift it to the right. If we do then subtract equation 1 and 2, what do you get? Well, all the terms containing R die out, and you're left with, on LHS, S times 1 minus R, and on the RHS, just the value constant A. What this means is that the sum S of my infinitely many terms is just equals to the constant A upon 1 minus the multiplicative factor R. Then say, what do you think about this cute harmonic series? Do you think it converges? Well, I guess, the terms are tending to zero at large values, right? So it should converge. I guess it converges. Aha, got you. Turns out it doesn't quite converge. Let's back up a little bit and see what we did with geometric progression. But I guess that was a boring way to do it, wasn't it? So then consider this. Let's say that you're eating nuggets in a geometric progression. What does that mean? Well, quite simply that in the first time you eat one nugget, then half, then 1 by 4th of a nugget, then 1 by 8th of a nugget, and so on. Note that each time that you're eating, you're actually eating lesser than what you ate before. In fact, half of what you ate before. Well, this is where I borrow your intuition for a moment. If you see, the way you're having nuggets is that you are having half of what you had before. This means that if you take a nugget and slice it into infinitely many pieces, then half of that nugget is your second bite, 1 by 4th of the remaining half is your third bite, 1 by 8th of the remaining of 1 by 4th half is your fourth bite, and so on. Then doesn't that mean that ultimately it should all add up to just 2 nuggets? Well, and it turns out that that's exactly what happens. If you take the summation of this series, you do in fact get a value 2. Well then, consider the same case as with harmonic series. You're having in the first bite 1 nugget, then half, then 1 by 3rd of a nugget, then 1 by 4th, and so on. So, while you're clearly overwhelmed by the amount of nuggets you get to eat, again it seems like you are eating lesser and lesser of a nugget each time, aren't you? I.e., ultimately leading to a portion tending to 0, isn't it? And yet, somehow, magically, this series does diverge. To understand how this really happens, let's consider the geometric series and the harmonic series. As you can see, I've written down both the series, but let's now look at it in the nugget language. So, compare each term of the nugget that you're eating in the geometric case as well as in the harmonic case. In the first one, you're eating equal amount of nuggets, i.e. 1 nugget each. In the second bite, you're having half nugget, again the equal amount. But note what happens from the third bite. In case of the harmonic series, you're having more of a nugget each time as compared to what you're having in the geometric case, i.e. 1 by 3 is greater than 1 by 4, 1 by 4 is greater than 1 by 8, 1 by 5 is greater than 1 by 16th, and so on. I guess you can already sense that there's something fishy going on. But let's dig deeper. Well, consider this new series which is so described that each term is some power of half, but with a condition that all of these terms should be less than or equal to the corresponding nugget portion that you're eating in the harmonic series, i.e. it should be less than or equal to the corresponding nth term of the harmonic series. Let's see how this happens. So in the first term, you're having 1 nugget each. In the second, 1 by half of nugget each. But in the third, note that the power of half, which is less than or equal to 1 by 3, is actually 1 by 4. So you're having 1 by 4th of a nugget, and then so on. Note that since each term of this new series is less than or equal to the corresponding term in the harmonic series, the summation of this new series should most definitely be less than that of the harmonic series. But wait, I think you're starting to see that there's something really cool about this new series that we have assumed. If we start clubbing the similar terms, we realize that all of them, it just so happens that give us half. Which means that the summation of this new series is just 1 plus half plus half plus half plus half plus half plus half, and so on. I can't do it forever, can I? Which means that it's ultimately just 1 plus 1 plus 1 and so on, i.e. you're adding 1 till infinity. What does that give? It means infinity, which means that this series actually diverges. And what does that mean? Since this series, the summation of this series has to be less than or equal to that of the harmonic, it means that the harmonic series diverges as well. But the more important implication here is that if you eat nuggets harmonically, i.e., one in the first bite, half in the second bite, and so on, you have the chance of eating infinitely many nuggets. And guess what? You can say that you're, health conscious as well because you're having lesser and lesser each time. But like that's so weird because even though the size of nugget that I'm eating decreases, yet I eat infinitely many nuggets? How weird is that? To understand how this happens, you need to know about this really cool guy called Auguste Louis Cauchy. Let's first formally put the criterion. What the criterion says is that for every epsilon greater than 0, there is a fixed number n such that mod of Sj minus Si is less than epsilon, where I and j are greater than n. To understand what this means, let's sort of plot what we expect happens in a series. As I keep adding more and more terms, turns out that my partial sums start getting clustered and start approaching a finite value capital S. So then, consider the sum value epsilon greater than 0 and the sum n. Now, Sn plus 1 minus Sn should be some value, right? And then Sn plus 2 minus Sn should again be some value. Note that all of these Sn plus 1, etc. are just partial sums. If I keep doing this till my infiniteth term, i.e. Sn tends to infinity, then S infinity minus S of n should again be some value. Why? Well, since S tends to infinity is just some value S. Then, for any epsilon greater than 0, I could always find some n such that S minus Sn, which is just some number, would satisfy my Cauchy criterion. To see this, I guess you'd have to zoom a little bit more on the cluster, but I'll leave that for your imagination. So then, going by what Cauchy gave us, consider the partial sums S2n and Sn. Then S2n minus Sn would just be equal to 1 by n plus 1 plus 1 by n plus 2 plus blah 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 going on to 1 by 2n. Note that there would be n such terms. Now, I can replace each of these terms by a term 1 by 2n. Note that since my denominator is greater now, then this series would most definitely be less than the series in picture. This means that I have n terms of the form 1 by 2n, which means that this is just equals to half. But wait, that means that if we chose our epsilon is equals to half, then as you can see, that S2n minus Sn would not actually be less than this epsilon, i.e. this doesn't hold the Cauchy criterion. And what does that mean? Well, of course, it's a divergent series. So I hope by now you have some appreciation of what convergent and divergent series are. And since you're still here, I'm hoping that your life's aim is eating as many nuggets as you can as well, just as mine. So why not eat infinitely many nuggets? So the next time a friend asks you for nuggets, you know how to reply back to them, don't you? Thanks for watching the video, and I do hope that you enjoyed it. If you have any suggestions, please let me know. I apologize if I was unclear at some parts of it, but know that I'm always ready for discussion. With this, I guess I'm going to sign off and leave you with this simple yet beautiful proof of the divergence of harmonic series by Nico Rochelsman. So I guess, namaste, sayonara, zaijian, bye bye, and don't forget, keep sciencing!